Hello students, welcome to my class. Today's class is on molecular orbital theory. According to scientist Hume and Mulliken in 1932, they have proposed the molecular orbital theory. So what is molecular orbital theory? To understand what is molecular orbital theory, you have to know about linear combination of atomic orbitals, LCAO method. So, if we combine two atomic orbitals of hydrogen atom, suppose one atomic orbital is represented by wave function psi a and another is represented by wave function psi b. That is psi a for atom A and psi b for atom B. So the resultant wave function psi m equals to psi a plus minus psi b, where psi b represents bonding molecular orbital and psi a represents antibonding molecular orbital. So when we want to get bonding molecular orbital, that is represented by the wave function psi small b equals to psi a plus psi b, and psi antibonding molecular orbital equals to psi of antibonding molecular orbital equals to psi a minus psi b. These are the addition of two wave functions psi a and psi b, which is represented by psi small b, and subtraction of two atomic orbitals psi a minus psi b equals to psi antibonding molecular orbital. Okay. So represent now let us represent in wave form. That is, this is represented by psi a. This is plus phase, this is minus phase, this is plus phase, this is minus phase. When we add psi a plus psi b, we get psi small b. How? These two wave functions are added here. These two are in same phase. Okay. Therefore, these two are added and we get the result psi b like this. Okay. If we subtract psi b from psi a, the resultant will be less than that in case of psi bonding orbital. Okay. Therefore, psi antibonding molecular orbital is represented by like this. Look at the atomic orbital A is represented by this picture. This plus sign means in positive phase. For atom B, there is also a plus sign. Plus sign represents the symmetry of the orbital. When we add two atomic orbitals, we get sigma 1s. That means two 1s orbitals. This 1s1 and this is 1s1 of hydrogen atom. Okay, we want to consider the fact of diatomic molecule hydrogen. What we will get? A plus B equals to sigma 1s, that is bonding molecular orbital. Okay. When A plus B with opposite symmetry, this is plus, but this is minus, we get the picture like this. This is sigma star 1s. That means this is the antimonadic molecular orbital of hydrogen atom. You see, there is a node in between the two nuclei. Okay, the nucleus are like here and here. In between the two nuclei, we get a node. There is no possibility or probability of finding an electron between the two nuclei. Here you see, here electrons are spread out over this region. Okay, the case of antimonadic molecular orbital of hydrogen atom, this is a positive symmetry, this is a negative symmetry, and there is a node between the two nuclei, and they repel each other. So they are far away from each other. But in this case, two nuclei are covered by the two electrons. This is 1s orbital of hydrogen atom, single electron. This another atom. This is so 1s. We will get this is the bonding molecular orbital. The antimonadic molecular orbital. These two electrons occupy the sigma 1s2, but not sigma star 1s2. Sigma star 1s, because according to Hooke's rule, the electrons will occupy the orbital of lower energy. This is of lower energy. This is of higher energy. Why? We have told earlier, in case of bonding molecular orbital, the work functions are added, but in case of anti-bonding molecular orbital, the work functions are subtracted. And when work functions are added, the energy will be lower, and when work functions will be subtracted, the energy will be of higher energy. Okay. So these two electrons of two atomic orbitals combine and occupy the bonding molecular orbital sigma 1s. So we can write the molecular orbital of H2 at sigma 1s 2 sigma star 1s